Cool. Hey, Hoagy. It's great to have you here. Um, so yeah, why don't you introduce yourself and tell people a bit about your alignment journey so far?
Yeah, sure, can do. So yeah, my name's Hoagy Cunningham. I am at the moment. I'm an independent researcher. I'm in the middle of doing Seri Mats, which is this kind of like researcher training course thing where you spend a couple of months in Berkeley, trying to do research, and then a few more months in London, also trying to do research with Lee Sharkey, who was one of the people who kind of originally set off the sparse autoencoders stuff. I was originally, I did like a philosophy and economics degree. Kind of realized that about 2019 that AI was kind of what I wanted to do, was probably the most important thing to try and help out with. So I went to Blackpool with Chris and with Greg for 6 months and worked on trying to build like AI safety courses. Eventually, the kind of funding ran out for that, and I went and got a normal job for a couple of years, and then about 18 months ago, quit that job and just sort of started teaching myself maths and programming full time. And then after a while, managed to sort of make some friends in the AI space and like work from like an office in London and sort of just start getting involved with projects. And first doing my own research and then kind of got into this sparse autoencoders stuff, which I'll go through. And yeah, now it's gone quite well. Got my first paper out and sort of yeah, now in a position to
Congratulations.
maybe apply to some of the big labs. We shall see. Um, yeah, just kind of not for any big belief in the big labs, but more just like the value of having a team actually working together on something, and not to mention computing resources. Yeah, I don't know how much everyone kind of knows about the like sparse autoencoder stuff. I mean, it's been
Don't
like
worry,
a
we'll get into that in a bit.
yeah, okay. So I can go into that, but yeah, that's my sort of basic background. Um, yeah,
Cool, cool,
I can.
cool. See, just because you mentioned the EA Hotel, Greg, do you want to interrupt this with an ad break for the EA Hotel?
Oh yeah, well actually we're in dire funding straits again. So if anyone fancies donating, we're going to be launching a fundraiser soon.
Sorry to hear that.
Yeah, but otherwise we're doing really well. We've like opened our next door building,
Oh yeah,
uh, got like three great part-time managers. Yeah, we just need the funding now.
Damn.
nice.
Well,
Yeah,
best of luck.
we didn't make the cut for SFF, so that's why we're kind of in a bit of a crisis now. But
Yeah.
Mm. Yeah, that's always tough. I'm glad the new building's finally there. That was just sort of brewing when I was there, I think.
yeah, we've got a doorway through to join the two buildings as well and making a courtyard in the middle. So yeah, looking pretty good. Anyway, back to scheduled programming.
Exactly. Yeah, exactly. So you said you studied economics and philosophy at first, and had you done any programming during that degree, or was it just
Uh,
afterwards I realized?
Not really. I think I did a little bit of programming when I was like 12, 13, but it never really clicked for me. Um, I think I had a Mac and like all the explanations were for Windows and I just couldn't like get the IDE set up and like I don't know, I just couldn't make that kind of like basic thing to sort of properly get the Python working and stuff. And I kind of at the time thought I would sort of be this like ideas person. I was like, I'll be the ideas person. And then these other people will do the programming for me. And that was how I'll be useful in various ways. And I started doing like projects with my friend who was a computer scientist. And it was just like really obvious that I would like have an interesting idea and then just have to wait and be completely useless while he like tried to like do something about it. And it was just like, obviously this is kind of stupid. I need to go and learn how to actually do something. So yeah, like pretty much immediately, I think I kind of during my degree realized that like, yeah, it was very if you want to like get any kind of fast feedback on something, like you should probably learn to program. And like yeah, so as soon as I left uni, as I think that was how I originally found like I think I was like trying to teach myself to program, and then I found Hacker News, and then I found Slate Codex, and then I found us wrong, and then I spent 2 months in a massive rabbit hole reading the sequences and such. And then at the end of it, it was like, right, okay, I know what I need to do. Time to time to try and help out with safety. That was the sort of conversion process.
So
But yeah,
yeah,
a few years of sort of on and off learning to program.
yeah. So you did it a few years on and off before you spent time at the EA hotel, or
That was a big part of the on and off. That was like a chance to I think I did just like little courses and stuff. I don't know. I'm quite like for someone who's been out of uni for like 5 years, I haven't spent that much time with like a proper job. I've spent probably 2.5 years or something, sort of in various ways, sort of doing independent research or kind of in between things, doing some courses, like doing some funny bits. So yeah, lots of sort of bits of time, and eventually you sort of get to the point where you like first you take on a project which you're like it's too much to do, but like the pressure sort of forces you to like try, even if it's kind of a bit embarrassing and you fail. Like I did AI safety camp one of those years, and someone says, all right, okay, go implement a machine learning model or something, and you sort of say yes, and then immediately run to anyone who could possibly help you, and sort of crank out something pretty terrible that doesn't really work, and someone else has to rewrite it for you. But it gives you the experience, and then next time you can sort of half make it work yourself and these kind of things. So yeah, but definitely I think the big one was like quitting the job and then being like, right, I'm going to give myself 3 months to re-implement AlphaZero, and just kind of sat at home like writing PyTorch all day until that kind of half worked.
cool.
Very very long time, kind of only ever half worked, but
And
yeah.
you have any advice for anyone who's doing anything similar?
The big one would be like really trying to find a place where people are like working on something even marginally similar. Like they're definitely the biggest like I did sort of manage it, like working from home and like working from the local library, like for a year or so, but it was pretty hard. And like everything got a lot easier when like I'm just lucky that I live in London by default, and there's like AI safety spaces and stuff. So like I managed to like talk to a couple of people who were like, oh yeah, we've got a bit of spare office space at the moment. You could just sort of come in and set yourself up. And like yeah, that's definitely how I like got into Ceramats and like sort of found out about a lot of these projects, and yeah, that made things so much easier. But even I think just like having some kind of office where people are doing something computer science related, some people who have a vague idea that you can like talk to yourself about is worth spending like a lot of your time networking to try and get that kind of thing if you don't have it.
Cool. That makes sense. All right. So let's get on to dictionary learning. So when did you become interested in dictionary learning?
So there was I don't know how many people have read the like there's a sort of classic Anthropic paper called Toy Models of Superposition, which is this really interesting, also in some sense it's very basic, toy models of tiny neural networks with 16 or 50 parameters, and they're just trying to understand, and the sort of basic idea is so yeah, you might have an input space with like 10 features, a 10-dimensional input space, and you force these networks to compress them down into maybe 2 or 3 dimensions, and you kind of see how this works. And because the big problem that Anthropic had been finding was that especially if you look at like high level layers in a vision network, or just pretty much anything in a transformer, you look at a neuron and you think, oh, this neuron is going to mean something. What does this neuron mean? And instead you get this sort of big messy smudge of it's activating on lots of things which don't seem to be related. And so they had this toy models of superposition, which explains that this is something that could potentially arise when you have like lots and lots of features, and you want to somehow compress them all into a lower dimensional space, a much lower dimensional space than the number of features that you have. And this only works if the number of features that are active is pretty small at any one time. If you have 2 dimensions and you have like 10 features and you want 5 of them to be active at the same time, this is just not going to work. You're going to have way too much interference. But if you have 10 features, 2 dimensions, but only one of them is active at the same time, then you can start to do something. And so I sort of reread this, and I'd also done some work. I just when I first got GPT-4 access, I like did some work trying to get GPT-4 to like explain GPT-2 neurons just before that very, very similar paper came out. And it was pretty clear when you look at like a neuron in GPT-2 that like, yeah, this is just not going to be right as the unit of analysis. So I was thinking about this and just thought, well, hang on a sec. If the sort of rule is there are lots of features, but a very small number of features active at any one time, like, can't we just kind of encode that in a network in some sense, and like see if we can use that structure to understand what those features are? So I was just sort of talking about this for sort of a couple of days to people in the office, and like strangely, I decided to call up. I just unrelated. There's someone, Baron Millage is someone who like was working at Conjecture at the time, very smart guy, and like I emailed him these thoughts. I think he was a bit confused because he was like, I'd accidentally sort of recapitulated or like had the sort of basic idea of a load of research that they'd done a few months ago. So Baron and Lee Sharkey and Dan Brown at Conjecture had just basically had the exact same idea a few months ago and had like sort of got halfway through implementing it. And then at Conjecture, basically Connor Leahy lost all enthusiasm for anything interpretability related. And so they were sort of like basically stuck, not working on it. And they had these kind of like unpublished, half finished results that they were kind of waiting for someone to take up the baton on because they were sort of doing other things. So it was like, okay, right, well, I'll take this on, I guess. And I got them to like publish their sort of half finished results. And then once they published their sort of, because initially they had a sort of post being like, here's an idea, here's some possible metrics, here's it not really working. And that was their kind of post. And they were like, by the way, we also just actually have some really good results. We just didn't publish them. And as soon as they published those results, like quite a lot of people started, looking at this and going, okay, there's something here. And so there was someone immediately who started replicating their work, and we like started chatting over Discord. We started chatting in public on the Eleuther Discord, and there was a couple of other people who came in and were interested. And then suddenly we had this little team of 4 of us, and yeah, we just sort of started working. Like, I think it just all. I mean, it's quite simple, Ultimately, the dictionary learning is quite, it's like 1 layer neural networks, 2 layer neural networks. So yeah, we just kind of started working, and in a couple of weeks we like replicated the Conjecture stuff, and it was like, right, okay, let's give it a go on some big models.
Cool. So yeah, we'll get into the technical details in a bit, but any chance you could just define superposition first, just for any listeners who don't know?
Yeah, so these terms are a little bit like contentious exactly which things are superposition. I think so. Superposition kind of comes in contrast to the idea, like, which has been a fruitful idea in previous cases, that like a single neuron has a particular meaning. We're like, okay, well, let's look inside a vision model. This is a neuron which detects curves. This is a neuron which detects wheels. This detects faces. And that's like how we'll understand this network. As you get more and more into it, you start to find that these neurons seem to represent multiple things. It might not be like this neuron is a total mush, but it might do wheels and noses and these kind of things, and maybe lots of those. And so this kind of thing of like, oh, we look at a neuron in a network and we find multiple things seem to be going on there. It is sort of the basic superposition. And this kind of gets a bit messy because often there's like that's in the case where you have neurons. You have like a 10 neuron, 1,000 neuron layer. And so it's somewhat reasonable to expect that when you have this non-linearity in the network, it's somewhat reasonable to expect that there's only maybe a single thing going on there. But you also have parts of networks where you have no reason to ever expect, like, you just have a 10,000 dimensional vector space. And if you pick any one direction, you will, of course, will find like a massive mixture of loads of different things. So sort of superposition kind of blends into this general idea that just lots of the time, the representation of something in a neural network is spread across many, many dimensions, or is in a particular direction, which is like not aligned to any kind of obvious basis. So if that's maybe a little technical, but yeah, I think super is just generally the idea that we're going to need to like, the sort of concepts are not just going to be at like nice, neat right angles in a network, and we can just sort of pick them out. We're going to have to do something a bit more clever than that.
Cool. So yeah, let's get a bit more into the technical kind of details. And so I guess the core of dictionary learning is a kind of an autoencoder where you have like a very kind of, a large kind of, layer for your intermediate layer. I don't know, could you explain that?
Yeah. So I mean, yeah, an autoencoder is usually something where you might take a lot of data and try and sort of compress it into a few dimensions. You know, might have lots of layers. You compress it down into a small number of dimensions, and then have a sort of separate network which then takes these small number of dimensions and is able to recreate the original image. And in doing so, you can kind of use this as a way of compressing your data into this, like really sort of tight form. So this is kind of a weird thing where we'll have our data, and what we'll instead of like squeezing it down to a small number of dimensions, we're going to like expand it out into this much wider set of dimensions, which is sort
Were
of
people doing that
matching.
before dictionary learning?
Um,
Is the thing, do you know?
Not really. There was so there's dictionary learning is an old thing. Like classic dictionary learning would say, okay, maybe we have this input, and this input is in fact composed of a sparse sum, a sum of a small number of entries from this really large set of things, this dictionary. But the sort of standard way to learn those kind of things, this is like an algorithm that comes from like kind of old pre-deep learning things like understanding vision in brains and stuff. And they would generally do it in this kind of like without using gradient descent or anything. You would sort of optimize your dictionary. You'd like have your whole data set. You would optimize your dictionary, and then you would optimize your like which dictionary elements do we sum up to make our examples of our data, and we would sort of alternate optimizing these sort of two things, our dictionary and sort of how we build up our data from our dictionary. And that was something which was used even in the sort of the most obvious previous literature for this stuff was a paper, funny enough, by Jan LeCun and others, a couple of years ago. I mean, a really good paper where they like took the residual stream of a transformer and sort of pulled it out into these sparse factors. They called transformer factors, which is ultimately really quite similar. But they did not use this kind of autoencoder method. It was just you learn the dictionary and you learn the coefficients from the dictionary to the data. But you don't have this, it's not a sort of neural network exactly. So I think that, I mean, it's such a simple idea that I wouldn't be at all surprised if someone has, it is just out there in the literature and we've not seen it. But yeah, I've not actually seen someone do that before.
Fair enough. Yeah, I'd really appreciate a link to that paper after this conversation.
Oh yeah, I can send over the Gun paper. It's yeah, really interesting.
Cool.
Yeah.
Yeah. And so I guess inside dictionary learning, you have two kinds of loss. You have like a reconstruction loss, and I'm forgetting the term you use, but and kind of, an L1 kind of loss.
Yeah, L1 penalty is the sort of thing. Yeah, you want to reconstruct your data, but obviously, if you're expanding your data out to an even wider space, it's totally undefined. The way that you like add some structure to this is to say there shouldn't be many things on, and if the most simple way you could translate that is to say, well, there shouldn't be more than 5 things on, or there shouldn't be more than 10 things on. The problem with this is that it's just not differentiable. There's no gradient from like how many things are on. They're either on or they're off. And so what you do instead of having this like how many things are on penalty is you add an L1 penalty, which is a penalty. Oh, we got.
Is that the paper?
I'm just posting the paper here. 2021 looks correct. Transformer visualizations. There we go. Yeah, that's the one.
Okay, cool. Need to check it out. So yeah, you were saying?
Yeah. So you use this L1 penalty instead, which is just sort of in your wider space, you just add up the level of activation of all of these factors, the sort of total size of your activations, and then you add that up, and that becomes your penalty. So you sort of you add that to the loss multiplied by some coefficient, and it's actually kind of weird because it's really not. There's like, I mean, the maths of it at first seems strange because if you have, in terms of sparse autoencoding, if you have two options, one where like a single factor is on with a magnitude of 10, and another one where 10 things are on with a magnitude of 1. The loss in this case will actually be the same. And yet what we're really trying to do is incentivize this 10K, one thing being on rather than the 10 things being on. But there is actually like a lot of mathematical literature suggesting that generally L1 minimization, like in like a pretty broad variety of scenarios, basically as long as the sort of true sparsity of the data is sufficiently high, and the features are sufficiently different, then the L1 penalty can sort of will provably be enough to recover the sort of like sparse solution. But it is a bit of it is a sort of kind of odd thing in a way that's how we're done, because we're not actually maximizing the thing that we kind of want in a weird way.
Yeah. So yeah, if you have the paper, that I'd be very keen to kind of check some of that stuff out. Because
The mathematics of it is I don't know if I have exactly a proper paper. There's a textbook on this stuff by Wright and Marr, like high dimensional data analysis with low dimensional models, and that's the textbook which has the I would say like chapter it's like 1 to 3 of
I've just posted an image in the chat with kind of my intuitions on why L1 norm favors sparsity.
Oh, nice. Yeah, those kind of diagrams are exactly the kind of stuff that is in Wright and Marr. There's like that and some like similar intuitions. But yeah, that's
Are you able to explain that diagram? Like, how do you interpret that?
Yeah, I guess you can see that like just one of the parameters in the L1 norm is maximized and the other one is 0 when you optimize for L1 norm.
There's this kind of like more generally, if you think of this kind of the L1 an L1 ball is like like you're finding the lowest L1 solution. So you can think of the square on the left as expanding until you hit hit something which is a solution. So the solution set is the red line, and the sort of idea is that for reasons I can't remember exactly right now, the solution set is definitely going to be a straight line. It's not a point. And so given that the solution set is this line, when you expand out your little square from 0, unless your line is sort of bang on 45 degrees, you're going to hit the line with, at first with one of your points, which is one of your like sparse solutions. And the sort of higher dimensional version of this is kind of messier, but like roughly the same intuitions hold. And I think it actually works generally better in high dimensions because, I'm not going to go into the high dimensional intuitions because they're very, very messy. But
so just to clarify, regarding the L1 loss, you're using it on the activations of the neurons. You aren't using it on any of the weights.
No, so that's a good point. So that there's one thing you might think is happening is it's definitely on those neurons. To do it on the weights would be to say that we think that the features should be quite localized to weights. So one thing you might think is going on is that like a feature is not maybe one neuron, but a feature might be across 5 neurons, not the whole 100 things. And if you thought this was really likely, one thing you might do is to put some kind of penalty on the weights as well, which would limit the number of connections from any of your input to tell like how many features should this one neuron participate in, and how many of our sort of learned features, for any one of our learned features, how many neurons should that correspond to? And if you think that number should be low, then yes, you should put some penalty on the weights as well. This is something I've been thinking about quite a lot because I really did expect it to be the case that this would be really helpful, and that features, especially in the MLP, not in the residual stream, but in the MLP, that features should be fairly localized amongst a small number of neurons. But it generally doesn't seem to be the case. And I've actually I'll be publishing a little post on Less Wrong, trying to explain why I think it's a little bit more reasonable than you might think that features are in fact potentially spread across like the entire layer. That Wright and Marr. Yeah. So I get the name high dimensional data analysis with low dimensional models.
That's pretty
Oh,
cool.
I got the high and low wrong. But yes, that is the textbook. And
Nice,
yeah,
nice.
really recommend the first couple of chapters of that.
Cool. So how does your how does your technique or your research compare to anthropics? I actually found a post that goes into a lot of detail, but it's just this thing like a huge number of differences, and it's not clear like what are the important differences as far as your kind of
Yeah, I still haven't read Robert's post. It's a bit embarrassing. Um, I sort of ran away from it for a couple of weeks. But so I mean, I think basically they're very similar. We did some stuff. I think one of the big differences is that they have a gigantic pile of compute, and so we roughly trained our things on 10 to 50 million examples per layer, where they were doing something like 10 billion. So there's like a scale factor of something like 500 in there, and I think that helps a lot. And I think what that does for their stuff is allow them to turn that sparsity penalty up quite a lot higher. So I think they generally have like much more precise features, so which then enables them to say, look, this is not just like significant. We were able to say, look, these are significantly more monosemantic than neurons or any like standard decomposition that you might do on these activations. Whereas they were able to turn up the sparsity to a point where you could say, look, no, actually, this is pretty much monosemantic. What they did as well was just to do it on a single layer neural network. So, just like a one layer transformer, whereas we were taking a sort of 6-layer pre-trained Pythia model. So I think we were doing it on a significantly bulkier model and showing that it was working at least up to the middle layers of that transformer. And like, although I don't think we had the sort of tools to really like prove it, interpretability is a very hard thing to sort of like prove in a single graph. But we were finding like interesting circuits, sparse circuits from somewhat complex high level behaviors, something that looks a little bit like a very simple version of induction, or like knowing when to sort of close a bracket, for example. We could see that there was a feature which was like really helping to close a bracket, and that there was sort of quite understandable features in previous layers which were contributing to this behavior. So I think we were able to show some degree of like, this is not just like sort of pulling out bits of data, but the features are getting somewhat more complex through the layers, as we would hope to see, and they sort of build together in some kind of meaningful way. I think that's something that's like still really underexplored, and like I know Anthropic will be doing a lot of that kind of stuff, and I think we're going to be looking into sort of how you can put out these circuits at some point. So those are maybe some of the biggest differences. They did their work towards the end of the paper in like finding these sort of automata type things. I think that was really interesting. That was not something we did. And they were also able to show sort of features. I think this is something that we both found, but I don't think we were able to show it so well in our paper, which is that what we didn't show in our paper basically was that we kind of came into it thinking that there might be this like a number of features. When you kind of like start thinking about why this might be a reasonable technique, you might imagine that there's like a certain number of features and we're going to learn those. And so we both spent the first few months of our research, or a lot of our research, looking for there to be a certain width at which you found like the perfect loss, and then below that, if you increase the width any further, you just wouldn't get any more features or something like that. And that's generally not what we found. It generally just seemed really continuous. And I think they demonstrated that well. But which is somewhat confusing. I think this is one of the big sort of theoretical kind of confusions about exactly how we should view this, because it doesn't seem like it's a discrete set of features, which is kind of the original motivation in some sense, but it does seem like the technique worked well. And like how we should visualize this kind of distribution of things, and like what mathematical framework should replace the set of discrete features, I think is one of the big questions, because we know it's not quite the right mindset to have about this thing, but it seems to be closer than any other kind of obvious kind of conceptual tool. So that's big open question for me.
Oh, okay, that's pretty interesting. So you said Conjecture had trouble at first, like their first results weren't that impressive.
They had. I think it's a bit confusing, to be honest, because our research, or at least the first like couple of months of it, did go very smoothly. I think they I mean, you do have to turn up the size quite a lot, like maybe unintuitively, like on the order of like, 10, 50, 100 million examples is pretty necessary. And so I think that they initially struggled to sort of, they like were going too small. And, I think if you kind of expect that, if you expect to not need that size, then they were finding that things converged very slowly. But I think with with decent utilization of a couple of GPUs, actually they converge in a pretty reasonable amount of time. I think in some sense their bigger problem was just the sort of organizational stuff that they were in an organization which wasn't really too keen on that kind of work and was trying to pivot away from it. So they had a few, like a month or so of troubles, I think, but nothing too crazy.
No, fair enough. Okay. I'll ask. Okay, one more question, and then I'll open up to the audience. So, in terms of like future research on this kind of stuff, any thoughts to share there? Like, what directions might be worthwhile people exploring?
I mean, since the Anthropic paper especially has come out, like lots of people have been excited about it in various ways. So one of the big things about research is like trying to work out what other people are not likely to be doing. So one of the obvious things is like, does this help for like lots of other little interpretability projects? I think that's the kind of thing that lots of people who are sort of doing standard kind of interpretability research will like start training these things and seeing how that fits in. So I don't plan on doing that exactly myself, but I think we are in a good position to like try and make sure that there is like a good open source, one good training code and two like pre-trained examples on lots of common models. So trying to make that easier, I think is like really helpful research. There's lots of interesting stuff to do in terms of scaling these things up and like really trying to find examples in interesting big models. At the same time, Anthropic are, as I've said, like I think I can say pretty confidently, this is like their big bet at the moment on interpretability, and scale is really important when you're training these things. So it's going to be pretty hard to like do something useful in that region. So that I would like absolutely love to do that, but that's like for me doing that is kind of conditional on me being at Anthropic.
That makes sense.
And so then I guess there's some like more theoretical ones. So one of the things you do, especially with MLPs, is like sometimes these features, your learned features, just start pointing in the wrong direction. Maybe they're just like not helpful, and so gradient descent just sort of points them to be like, you're not being helpful, just shut up, basically. And once it's sort of not getting, once a feature is never turning on, it never gets any gradient, and so this is like it's a tricky place. And so what you need to do is like reinitialize features sometimes. And we didn't really get this working, but at the scale that Anthropic did, where they were like really turning the sparsity up, this becomes a bigger problem. And so they have some ways to reinitialize. I don't think they like found the right way, and I've got some ideas about how we can maybe do that better. So that's something that I might do over the next few weeks. I think for someone on the outside though, other than just sort of trying to use it in projects and seeing when it works and when it doesn't work and trying to really understand it, like how useful that as a tool really is it. The sort of theory of it, I think is maybe the biggest thing. Like how should we view, like I was saying, like what is the conceptual tool that we should use to understand these things? Because we don't have the right framework to think about it. I think that's making it much harder to like make progress around, what potential improvements to how we train these things.
Cool. So I'll open up the floor to questions. Feel free to just use the hand up feature. Like if you go to the bottom, I think. Okay. Is there the reactions feature? Yeah, you can raise your hand if you have a question.
EJ?
So I was just wondering whether I can understand the I guess the architecture a little bit better. So the sparse autoencoder, is it just like two layers? It like starts small, it expands really big, and returns to the original size?
That's absolutely it. Yeah, there's like it's two big matrices and a ReLU. That's all there is. And in some ways, so I think it's necessary that the second half of that, from your wide space back to your input space, I think it's necessary that that's just a matrix, because you're kind of saying that you're saying what's going on is just that your input is a sparse combination of sparse linear combination of these features. So that's, I think, necessarily simple. There's like some debate about whether or not the encoder needs to be so simple, or maybe actually you could do something more interesting by having maybe multiple layers there and saying, maybe we can do some kind of more subtle decoding than just some kind of like linear plus ReLU. I think that is maybe possible, but I also think that the neural network basically has to work consistently by these kind of tools where like it's if information is going to be available in a layer, it's going to be available by being sort of able to be pulled out by just sort of rotating it into a certain basis and then kind of chopping it off. Like that's the main tool available. And so I think having this really simple structure kind of like mirrors the way that neural networks tend to make information available. And that's a kind of strong claim, and I can't prove that. But empirically, when we did try to like make the like encoder section more complicated, we generally didn't seem to get much results. And maybe a better engineer would be able to, or find there's just some trick that we missed. But as far as we know, yeah, the kind of simple setup seems to be the one that works best.
Cool. So just to clarify stuff, so I guess generally in terms of terminology, you would say that it has one layer. It's this weird thing where you would say that this is a single layer, multi-layer perceptron, which is absolutely terrible terminology, but that's what we call it.
I mean, I wouldn't even, just like matrix, ReLU matrix is like, is the least ambiguous way to talk about it, I think. Like, yeah.
And in terms of the data that goes into it, it's activations from a GPT model, that kind of thing. And what is the GPT model fed with to make these 50 million examples?
So, I mean, as far as I know, we've not found like huge differences. I mean, it's not something we've looked at, like whether or not different data sources make a big difference. I think by default, we worked with the pile, which is just a big load of open source data. Like roughly we kind of want to match to the like training distribution to sort of capture the full range of behaviors. So we're just gonna feed in thousands, millions of tokens, use something like transformer lens or BowKit, or I think even the just transformers library does it as well, and like pull out the activations at this particular layer that we care about and then feed that in. So just sort of activations from the distribution. And I think it's a big open question to what extent you really need to go for that. We need the sort of like whole training distribution, or whether you can say, look, this is the kind of behaviors I'm interested in. I'm just going to feed it tokens from this kind of behavior and run it on that. Or do you really need to do this kind of pre-training? And my money is kind of on the pre-training, but I'm not certain. So yeah, that's another thing that I'd be interested to see.
Slava.
So I guess Anthropic applied the autoencoder to the MLP activations, whereas you did the residual stream. And so do you see the Anthropic approach scaling to multi-layer models? So where features can be split between MLP layers. So if you're applying separate autoencoders to the separate MLPs, your features can fall through the cracks, whereas your approach of residual stream should probably get around that. So what do you think?
It's really, so we did do stuff on the residual stream. So what kind of happened was that and I think this was related to like training size, like amount of training data, because it was still going up at the end of our training data. But we did we did residual stream and we did MLP. But what we found with the MLP was that at least at the like training scales that we were working on, we were not robustly, like the early layers we were finding overcomplete bases, but we weren't finding overcomplete bases in the later layers, though the number of active features was still rising. So I think if you turned it up by like 1,000 times, you would probably be fine. And so we did generally find this worked like reasonably well in the middle layers of in fact, it worked as well as it did it anywhere else. In non first or last layers of the MLP of like a real transformer. So I think empirically there doesn't seem to be this issue where it's just like impossible to deal with it. I think like theoretically it's a really weird question. Like clearly what it's doing in some way is like, yeah, it like generates features over lots of different layers. So like, you know, when you see there was that paper where they were like finding the longitude and latitude directions, and you can see these things being like gradually constructed across lots of layers. And like what that should look like in terms of a sort of sparse autoencoder is unclear. I mean, I think like, yeah, how that it's kind of weird because there's clearly, I think there's definitely structure that it doesn't pick out, because what you have is you're picking out all of these kind of like kind of lumps in the data distribution. If you like sort of just do it on the input, you find the lumps are like just the tokenization, and then it's going to sort of like slowly kind of like fold and reshape this input distribution into different shapes. And what you're going to do is sort of find the lumps at all these points, and I guess these things sort of, I guess, correspond to sort of yeah, something like features. But what you're also seeing is that the ways in which these directions are arranged are going to be constantly being manipulated through the layers, to get to the point where it's possible to make some developed feature, you know, some sort of like fully formed feature down the line. And so what I would guess is happening is that even though you might not see this feature emerging as like a distinct lump at some point, the kind of space is being rotated and sort of reshaped in ways that the autoencoders aren't able to pick up. And then I guess whether that like then sort of emerges in a clean way later on, or whether that those sort of emerges like less clean features early on, I don't know, to be honest. Yeah, I think it's a really interesting point.
Cool.
Jordan.
Yeah. So I just want to check, is the loss function just the reconstruction error of the activation vectors plus L1 norm of the sparse features?
Yeah, that's the standard. Yeah, I mean there are sort of potentially other things that one can include, like we were talking about previously. We tried like some level of like weight based penalties as well. I think we tried a couple other loss penalties that I can't remember right now. But yeah, that's the like simple default version.
I'll just add a quick note. I saw an Anthropic paper where they I think it was Anthropic, or was it you guys, where they tried a bunch of more complex stuff, and they're like, actually, we decided to go with the simple thing at the end.
Yeah, no, that was definitely that was the Anthropic one. Like, I think I don't know how much we influenced them. I think we tried this simple thing first, and we're like, well, this works, and we did a little. I mean, Aiden especially did try a few other things, but we mostly stuck to this kind of basic one. Whereas I think it went initially for this the kind of like previously existing dictionary learning approach, which was not via a neural network. And I think I don't know how much they were always had this sparse autoencoded stuff in mind versus like saw our results and realized that was going pretty well. But yeah, they definitely tried a lot more like other bits.
Well, actually, yeah. So I'll actually toss in a question. How much did you talk to Anthropic or those guys while you were working on this research? Oh, damn.
RIP.
Okay. Okay. Hopefully he's back in a second. We'll see. Yeah. I mean, I guess let's see what's happened. Did any messages, anything? Uh, yeah, I don't have any messages. What were you going to ask anyway, James? We'll see if he turns up again.
Yeah.
But
How do you, if you're using an L1 penalty, how do you stop the model from just moving all the weights to the decoder weights?
ooh,
So like obviously if there's a sparse activation that's 10, the L1 would want to make that like, yeah, if the sparse vector is 10 0 0 0 0 0, the L1 penalty will want to push the 10 down to 0 as well.
Yeah, so what you're saying is it would want really tiny activations and really large decoder weights, right?
Yeah, yeah.
Yeah, so
you just
in
make the
Neil's
matrix
code,
orthogonal?
yeah, in Neil's code, he regularizes the decoder norm to 1. So that's a neat trick.
The decoder weights, the norms of
Hello?
the weights are forced to be 1.
Yeah, this is true.
Yeah,
Sorry,
yeah.
I've lost track of battery.
Hey, good to have you back again. So, James, why don't you repeat your question?
It was basically answered, but the question was like, how do you, if you're using L1 norm, how do you stop the L1 from making the actual sparse activation you want to be really small?
Yeah, I just got the end of it. Whoever said that is bang on. Yeah, you just normalize.
Cool.
You make sure that the size of them is always normalized to 1.
I have another
Do
question. That's
you,
okay.
do you normalize the weights with L2 or what do you normally do?
You set the thing that you want is it's the of the decoder. So when you're going back to your input space, you want to say that those things all have unit norm. When you interpret that each feature as a direction, you're going to say that the size of this direction is 1. So yeah, like the square root of the sum of all the squares of the elements. You set that to be 1 at every step.
Cool. So,
I think there's some clever ways of like making sure that didn't like weirdly affect the gradient, which I think we never really implemented.
okay, so just to check, so you're trying to force the norm to be 1. So that mean you're doing like a gradient descent with like a kind of a extra condition?
Yeah, I mean, I think we were never too sort of clever about this. Really, we would do the gradient descent step, which would include like altering the norm of that direction, and then we would just immediately before the next step set it back to 1, just rescale. I think maybe there are like slightly better ways to do this, and I think they did sort of find some, but I don't think this was like a huge problem.
Cool. I can see your hand still up, James. Did you have something else to ask?
Yeah, I was curious to hear to what extent, because obviously Lee et al., as you mentioned, has been looking at sparse autoencoders for quite a few months before this Anthropic paper. It seems like when the Anthropic paper dropped, there was like quite a bit of hype, at least on Twitter that I saw, about what was happening. To what extent was it, do you think, that hype was a function of like the Anthropic name versus like the novel things they had in the paper?
I definitely think that. Yeah, I mean the paper is really good. It's hard for me to tell because like obviously like for me and like I was working on this stuff for sort of 6 months, so like the Anthropic paper was not like a huge exciting update for me. I think the level of monosemanticity was exciting, and there was some, but like largely, so yeah, it's kind of hard to sort of imagine whether that's. I mean, I think people sense, and I think Anthropic are very excited about this. And when people like Chris Ola and stuff were saying, look, this is like what I thought might be the biggest blocker to interpretability, and like, it turns out maybe we think this isn't actually a huge issue. Like I think that is like a big driver of hype, and that's like exciting. It's exciting for me to hear that because like I think they have lots of like private information about additional experiments and scaling up already. I imagine that I don't have access to. And I think a lot of people kind of had internalized the superposition thing as like the big issue with just sort of going through and let's just interpret a neural network. I think definitely there was a lot of hype which like kind of got out of control. Like I mean, I think a big thing is going to be like relating like assuming that this works perfectly and you like understand the way in which like features are built up. I'm almost certain that this will end up like missing a lot of interesting behavior, partly for the reasons I was saying to Slavos. He mentioned, you're going to construct features over multiple layers, and it's not clear how this technique in its current form addresses that. But how you're going to relate that to actually trying to really make a model safe, like acting over long time scales in complicated environments, like bridging the gap from this kind of like super low level behavior to that kind of stuff is a huge deal. And like not, I don't know, I don't think, yeah, we don't really have even the sort of language to like think about how to really like work on that kind of stuff yet. So I think some definitely like the upper end of the hype was overblown, but I think it is in fact, like assuming it holds up and that it is actually turns out to be useful, and no one says, look, this is actually just how it's like finding patterns in the data, which I think Anthropic also showed is not really true. Yeah, I think it's reasonable to be pretty hyped.
Cool. Anyone else have any questions? I should just note. Okay, cool. EJ. Yeah, we're getting towards the end of it. Do you have to leave on the hour, or do you have a few more minutes after that, Hoagy?
I feel like I should probably go to work. Sorry, it's 10 a.m. on a Tuesday for me. So like, yeah.
Cool. Okay, last question then. Okay, EJ.
In like the circuits analysis by Chris Oler and stuff like that, they found, like the curves and the cars and that kind of thing. With this, have you been able to find like human decipherable like concepts?
I mean, I think in some sense, definitely yes. I don't think there's necessarily that exciting. And one of the tricky things is like, obviously, I mean, you get a human decipherable concept immediately from if you look at the directions in the embedding space, right? Immediately you like get interesting clusters and these kind of things. So in some sense, finding just human decipherable concepts of like, oh look, this is activating on chemistry words, and look, this is activating on like dates and these kind of things. You definitely do that. If you get that from the embedding, and like if you look at medium layers where you've started to incorporate information from previous tokens, like just to like understand this is not a random number, this is a date, is in some sense like a or a year, or these kind of things. That's like a human interpretable feature, and we get a lot of those. I don't think we've not like got to the point where we can sort of go through and like classify all of these things and be like, look, here is the range of concepts that this thing is pulling out. I mean, we like, or either doing it by manually or the sort of automatic interpretation. Both of those things are both pretty expensive and long. So, and I think we would want to like make at least our autoencoders better before we try to really do this kind of like full suite labeling. So yeah, I don't think we can quite. I think it's like now possible, but we don't have like the equivalent to sort of circuits for at least like the early layers of these models. I think the later layers is there's still. I think I get at least what I got the sense was like the early and middle layers. This seemed to work quite well. If you looked at it manually, the later layers did kind of look okay. The automatic interpretation didn't look great. I think there's still definitely some degree of like mystery of what's going on in there.
Cool.
But yeah, I think maybe a year you might see something like, a pretty solid full circuit analysis of something like GPT-2. Hopefully.
Cool. Thank you so much, Hoagy. It's been like absolutely great having you here. Really exciting research. Was great catching you when I was in Berkeley, and hopefully I see you around in the future.
Yeah, well, if anyone's in London, I'm always, well, who knows, but yeah, I'm around now. So if anyone wants to like, catch up, whatever, just give me a bell. And yeah, thanks for inviting me. It's fun to see, fun to talk about. Hope curious what you're all working